So it's great building from what you've already heard with these folks. What I'm going to talk today about is really a decision support tool for farmers and water managers for implementing FloodMAR. The tool is something we have up and running in the last year called Groundwater Recharge Assessment Tool. And I think these I did that. Yeah. We've seen the graphs before. We're really looking at what are the opportunities for replenishment of groundwater and also trying to avoid the damage from flood events that would cause damage to cropland or other uses. The concept that Helen presented, and actually everyone's been talking about, of on-farm recharge, really the concept here is how can we reconnect the rivers to their floodplains in a way that's managed and controlled. And we have the great advantage of having a canal infrastructure system that is in place to be able to divert that water out rather than simply giving up the levees. We actually can move that water to suitable locations if we can plan and identify the best places and the best timing to cumulatively capture those anticipated flood flows. This whole concept requires quite a lot of research. The work that UC Davis is doing is really critical towards that. We've also been doing an additional number of sites. We've got 6 research sites on almonds, grapes, pistachios, where we're also collecting data, working with Bashand and Associates here in Davis, who actually started this idea back in 2011 with a farmer, Don Cameron, really who had been pioneering the concept for quite a while and was viewed by his neighbors as somewhat crazy for taking all this floodwater off the river to avoid the levee collapse and putting it on his farmland. And what we've been able to do over the last 7 years is start to document how much water he has taken and what the crop effects have been on his lands. He's probably one of the more aggressive rechargers out there right now. Others are more conservative, but there's really quite a range. Plus we have about 200 sites where water was taken for recharge this past winter that we're getting data from the irrigation districts on to understand which crops at which time and also at what cost, because there is a cost to taking this water, and that's certainly a factor. And in fact, these are the factors very similar to, I think, the flower image and some of the other ones we've seen, or Helen's list. The growers have to be interested. So having information that gives the growers confidence that this is not going to destroy their crop is critical. Site suitability, we've already heard and talked about. Crop compatibility is really a big factor that is not fully researched. It's really in its infancy, I would say. Conveyance and water district support is critical in terms of a lot of times these canals were used during the winter was the maintenance season. So being able to use them to convey flood flows can be a disruption to those other operations. The water storage cost comparison, John, your conversation on that is also interesting. And then ultimately, what kind of flood management mitigation can we achieve from this? And what's the economic value of that that could be a potential incentive to districts and landowners to take that water? So the groundwater recharge assessment tool is something that Sustainable Conservation has developed in partnership with another nonprofit, the Earth Genome, which is a data management organization looking at how do we make public data more accessible and more useful to decision makers. And the purpose of the tool really was to identify the most cost-effective alternative combinations of both dedicated recharge basins, which a lot of water districts already use, fallow land recharge, and permanent cropland recharge to capture available flood flows on a weekly basis on the water sources. We worked with 2 districts after interviewing a number of them that really wanted to see this tool developed and had these really key questions about these essential investment choices that they have to make around what's it cost to take this water, how much can they in reality capture, when and where, how much can they capture, and ultimately what portion of their groundwater overdraft can they address with this. As Romain said, the agricultural and water communities right now are really concerned about the trade-off between how much more supply can they generate versus how much demand reduction might they have to carry out. And demand reduction is the last thing they want to do. They really are interested right now in this recharge potential. So the conceptual model for the tool is that it takes water availability, and I'll talk about that in more detail, but essentially it's the surface water that's available to the district from all of their intake systems, that it doesn't withdraw environmental flow levels, doesn't exceed environmental flow requirements, and also is within their water rights. So within that, then, the water that they can take is run through their district conveyance network. And the conveyance network then identifies where all the potential recharge locations are, but also defines how much water you can actually put on any given field in that district. For each site where water can be conveyed, we use public data around site suitability. So it's soil data, the SAGB data that Helen described for the topsoil. It takes CVHM data for coarseness. It takes DWR, depth to groundwater data, and the presence of Corcoran clays, and then overlays with that the crop that's currently on that land and how much water can that crop take based on best available knowledge right now, both field-based and emerging science. And allows the user to define, do you want to use recharge basins, or do you want to use on-farm or fallow fields, and run various scenarios with those options, each of which have cost implications, which can then be linked to the cost of that recharge system. So the tool it's a cloud-based tool. It's controlled access for the districts that currently have loaded their data into it. They have passwords to get into it because of the nature of some of the information and the costs that they're using in there. The model looks at all of the fields within that district. So typically 2,000 to 3,000 individual fields. These are unique crop land use fields. And the tool automatically ranks them in terms of these initial 3 suitability. This seems to be on automatic. High suitability, moderate suitability, and low suitability, based on those factors I talked about before, the site suitability, the conveyance capacity to get the water there, along with proximity to the edge of the district, because there's concern about losing the water outside the district, and deep percolation. It looks at that. The conveyance networks are in the orange squiggly lines across here. It also allows a whole variety of other overlays around disadvantaged communities, all sorts of other public layers that can be looked at just for reference sake. This is a look at that same district using the land suitability, which is a combination of SAGB, which from UC Davis, along with all those other factors of CVHM and depth to groundwater. So within the district, you can see the areas that are darker green would be better suited locations, but then each of those fields have different crops on them, which also affects that suitability. In terms of water availability, because there really isn't a great system out there yet, and actually Helen's new system is going to become, I think, quite valuable, but what the districts told us is they don't know what their future projected water availability is going to be on their input sources, both from streams, but also purchased water through Friant canals, other conveyance systems. So what they asked for was the ability to set their water availability on their own for the next 20 years, and they can use either historic records, worst case projected drought conditions, expected intensity, greater intensity storm events, and they plug them in based on DWR water year types. So there's the 5 water year types here. And they can set the number based on their historic wet, above normal, below normal, dry, and critical type years, plug in the 20 years of those as they want to project various scenarios. The tool, part of the data loading for this is looking at each of those water year types is what's the distribution of that water through that water year type, and how much of that water is already called for either for irrigation purposes, which is the brown here during the growing season. There's a lot of that water is already being used, and there's also baseline environmental flows requirements. So it's the difference between those other two that is really the water available for recharge on a monthly basis, and then we break that down into weekly availability as well. The grower or the water manager then determines the type of recharge they want to consider. They can select basins or fields in different types of crops. And I just want to say a word about the crop compatibility piece of this. At the time we built the tool, there was actually very little published material out on the calendar. So we actually went to the farmers that had been practicing it and their agronomists to find out what amount of water would they feel comfortable putting on a field in excess of what the crop is currently using for crop demand. So they're in weekly time steps in terms of inches of water that you could put on that field, all of them assuming those top two categories of SAGB. It's got to be well-drained soils. This is clearly going to need updating. Some of our field work is showing this example here of grapes being flooded and starting to see some crop effects. That's clearly too much water. So the numbers we used are much more conservative than what's actually being done currently. So then the tool's ultimate function is to be able to plug in how much water you expect in a wet year, how much is lost through seepage from through the canals, and then how much do the selected sites that were needed actually capture. So it takes on a weekly time step, finds the top rated fields, puts as much water as that crop can take in that week, and goes to the next one and just works its way through optimizing sites through the course of the year. It also gives costs in terms of operating costs for both the basins and the cost to the farmer of doing this type of recharge. It ranks all the fields. Individual fields can be removed if the farmer's not interested, or added if they are interested, to run different scenarios. And it gives models, or it gives results then that allow evaluation of, over the 20 years, how many years do we actually have net recharge above annual groundwater pumpage that was used as the baseline. And under sigma, this line, this historic without recharge line, really needs to come up to being a flat line. And in this particular scenario, it's some improvement, but not enough. So the tool can either be rerun, increasing the types of recharge that they want to practice, or they can change the pumping rates to find out what it would take to actually become groundwater neutral over the 20-year period. And really part of the purpose of this is to engage stakeholders in the conversation about the trade-offs. Do you want to reduce pumping? Do you want to practice more recharge? What crops are you willing to practice this on, and at what cost would it be? So over the 20-year period in this scenario, $17 million investment needed to compensate the growers and cover the recharge basins currently used. Is that worth it to try and achieve some level of balance? And then sort of to the question that we just had earlier, it's mostly designed as a planning tool, but the water districts that are using it are starting to see it as an operation tool as well, that they can actually plug in. If we get a water release next month of 40,000 acre feet, what are we going to do with that? Where could we put it, given the time of year that we're in now and the crops that are in the ground at this point? Are there adequate place to put it? So I end with that.